Okay, conservation of momentum. In a sense, we could derive this based on what we already have with the impulse momentum theorem. We could talk about how the integral of force with respect to time is equal to the change in momentum, and if there are no external forces, then we just get the change in momentum is equal to 0 for our system. It's not necessarily the most satisfying way of thinking about it, so let's take a look at another way. We'll set up a couple of objects that are undergoing a collision with one another. I wish this worked a little bit more easily, but there we go. So here we have an object 1 and an object 2. And there's going to be a force on object 2 due to object 1, so force due to 1 on 2. And there would be a force due to 2 on 1. And we're going to use Newton's third law here. So what we know is if we take F12 and we add F21, we should be getting something that looks like 0. All right. Now, in each one of these cases, we've got a mass 1 acceleration, well, we've got a mass 1 times acceleration 1, which would be equal to the force on 2 due to 1. So that would be an M2A2, and then we'd have an M1A1, and equals 0. All right, we can divide this up. We'd have M2 dV2 dt, M1 dV1 dt equals 0. Okay, and let's see. I think I'm on the right track, but I want to check something. Yep, doing fine. Need to have more confidence. D by dt of M2 V2 plus M1 V1 and equals 0. Okay. All right, what did I do here? Well, I just took advantage of the fact that M2 is constant, so I could pull it inside. M1 is constant, so I can pull it inside, which means the derivative can be pulled all the way out in front of everything else. So d by dt of the quantity M2 V2 plus M1 V1 equals 0. All right, we're going to do the separate and integrate thing. So we have dm2 V2 plus M1 V1 equals to an integral of, well, equals to 0 dt. Okay. So if we integrate this, we're just going to get that M2 V2 plus M1 V1 is going to be equal to, well, I suppose plus a constant, is going to be equal to 0. So in the end, we have M2 V2 plus M1 V1, our system, equal to a constant in terms of its size. Whether it's plus or minus doesn't really matter, just remember constant is constant. So the size of it isn't going to change. All right, and granted I've got them in the backward order from what we're used to, but this works fine. Okay, so momentum is conserved. That just means the total amount of momentum the system has doesn't change with time. That's going to have some very interesting consequences. If when we start looking at center of mass, it's going to mean that the center of mass keeps moving the exact same way, even when a collision occurs, as shown in this picture. This is showing a collision occurring. Next up, we are going to talk about collisions, particularly types of collisions, and then we're going to move on from there. Right, I think this will do, so I'll stop here and we'll come back for collisions.